let's take a look. So when it comes to the dilations, x dash y dash stuff, they're always multiplications on the variable themselves, right? So there's a couple of ways that you can word it. You can write it as a dilation along an axis or from an axis. Depending on which keyword you use there will depend on if you're going away from the axis or along the axis. So for instance, for it to impact the y variable going in the y direction, you can think of that as either traveling along the y-axis or going away from the x-axis. So that's one of the things that gets students a bit confused, which is whether using this or this. The textbook will exclusively use from the axis, but I've also written along for two reasons. One, because it's valid, you can do that. And two, because I feel like it's easy to just say, hey, this is the direction we're going, so I should say that axis. But whichever one makes most sense to you, you can work with that. As for how you actually apply the dilation, it's a matter of whatever axis you're going in the direction of, the factor is a multiplication on that variable. So you have your initial x, xy, and then your x dash y dash. Your, in this case, y dash is now going to be a y, where a is the dilation factor in your scenario. So that's going to give you a few equations that you can create there. So x is going to maintain as just x dash because there was nothing impacting the x. Y dash is going to be ay.
Okay, so we um y dash is equal to a times y. That means it's a dilation from x-axis.
Yep, dilation from the x-axis of factor a.
Okay, so it's multiplying the whole equation with a.
Yeah. So if you see where it ends up in the entire, after you go through the procedure of x dash y dash, you'll notice that it's a multiplied by the entirety of f of x.
Okay.
Yeah, that's how that one works, at least in the context of the y dilation. If you have a number bigger than 1, it'll stretch further along the y-axis. If it's between 0 and 1, you'll actually see it shrink along the y-axis. So here's a quick example, right? Applying a dilation factor of 2 from the x for this particular function. Well, dilation factor is 2, so you're now going to have 2y. Again, it's from the x, away from the x. You do your rearranging to get the x and the y back on their own, and then you shove that back into the function. So you had y equals root x. This is the only thing that ever changed. Just make sure you drop off these dashes when you sub it in. And then, yeah, so the y over 2 now becomes over here. Just put the 2 back over to the other side. We're looking at these in isolation. You wouldn't go through all of these steps just to apply a dilate factor of 2 if it was just this level of complexity. You'd more so follow this sort of thing when there's like a sequence of transformations to do, which is why I've got the shortcut here as well. It's like, hey, that's how you apply y dilations. Just shove the whatever the factor is at the front. Along the x or from the y is pretty much the same thing, but it's going to apply to the x. Now, the thing that's going to look a little bit different is once you go through this full procedure, what you'll realize is that when it's fully simplified and everything's on the right side that it should be, dilation factors that are in the x direction appear as divisions in the function itself. So it's a little bit weirder because if we look at like the procedure, you have the multiplication on the x to start with, it flips to a division, and then when you shove it into the function, there's no further rearranging to be done because the y is already on its own. Whereas when we had the y one, it was a multiplication, then a division, and then because it was on the left-hand side, it flips right back to being multiplication. So this kind of gives you a bit of an appreciation for why that's happening. So just to observe that if it's anything like x related dilation wise, you have to rewrite the thing as a division rather than a multiplication. So for instance, if this said 2x in here, that's not a dilation factor of 2, that's a dilation factor of a half. So you need to rewrite that as dividing by a half.
Okay.
Like here, right? So we're applying a dilation factor of 2. When all is said and done, it's going to appear as x over 2. That is distinguishing it as a dilate factor of 2. Fair enough?
Yep.
Cool. I mean, that's dilations there in isolation. Was there anything in particular in like the textbook you were looking at?
I guess applying the recognizing transformations. I'm kind of struggling with that.
Recognizing them as in when they're already in the function?
Yeah, like
Yeah.
from going from one function to another.
Oh, going from one to the other. Okay, so that's the determining side of things. So that's when you have like this sort of thing going on. You got a big f of x and you got another g of x, and you want to figure out how to go from one to the other.
Yeah.
Yeah, cool. Let's do that. So here's the full procedure that you can follow for that. Again, there's a lot of text there, but it is the stuff that if you do this over and over again, like these are the steps that will work every single time, as long as you know where you're starting and where you're going. I've got a few examples in here. They are technically the same thing though. It doesn't really matter if you start from transformed and go to an untransformed state. You could do the other way around. They could even be both in a sort of transformed state as well. I think I've seen an example of that. Chapter 3. I think it's in here somewhere. Transformed and transformed. So it doesn't really matter what both sides look like. The only reason I have both of those examples in there is because it'll slightly look different in your, this 3B step, but we'll see that when we get there. So first up, what do? We want to start by identifying where are we starting and where are we going. In this case, we're mapping the function f to the function g. We're starting at f, we're going to g. The way you, it doesn't really matter how you track this, but if you want to use proper math notation, what you'll do is you'll give x dash y dash to the function that you're heading towards, whatever that one is. So g of x is going to be rewritten as y dash equals 1 over x dash squared. X and y is going to go to the original function. So instead of saying f, we're going to say y, and well, x is still just going to be x there. Cool so far?
Yep.
Next up, for both of the functions that we see, every transformation factor that affects the y is going to go onto the y side, and everything else is going to stay on the x side. We see there's a vertical translation of 6 here, and we see there's a dilation factor of 3 here, both of which are y transformations. I know one of the things you said was recognizing it is a bit harder. Are you able to understand why those are what they are?
Yeah, I think so.
Okay, that's good. If there's ever any confusion as to what's a y transformation and what's an x transformation, the advice that I give is shove everything over to the left-hand side until the right-hand side stops looking like a basic function. So for instance, you could move this 6 over and still have it look like a truncus. You could move the 3 over and still have it look like a truncus. You can't really move anything else before it stops looking like a truncus at this point. Like expanding this out doesn't look like a truncus anymore. There's no further rearrangements to be done that would keep its basic form. And if you follow those rules, you'll get everything you need. If both functions are transformed, make sure you do it to the other one as well. In this case, we're looking at a bit of a simpler example, so there's nothing left to be done on this side. But if there were stuff there, you would do it to this as well. Next, we're going to draw some equivalences between them. So essentially, you look at the left-hand side of one function and compare it to, make it equal to, the left-hand side of the other function. Again, if this one needed rearranging, you would compare it to the end result, not the starting result. So essentially we have y dash is the same thing as y minus 6 over 3. We got that comparison. From there, you got the right-hand side and make it equal to the right-hand side. So the one from this one equals that. I should probably rewrite these notes because that's the easiest way to think about it. The reason why I was able to go straight to just saying x minus 1 equals x dash is because technically speaking, you don't really care about the entire right-hand side. You just want to contain all of the transformation related data or related information. The fact that it's a truncus means nothing at this stage. We really just care that this is a shift right by 1 and this has nothing on it. And so we're actually technically just supposed to be comparing that information. But it also works out to be the case that if you do equate both right-hand sides, you'll still get there anyway, just with a few more simplification steps. So this is more so a shortcut as you get better and better at doing these. If you're still like trying to get the basics down, just make right equal right, left equal left, and take it from there as far as you can. Make enough sense?
Could you explain that again? I think I lost my train of thought.
Yeah, that's fine. So basically, as of now, we have got all the y transformations onto the y side, and all the x stuff is on the x side for both of our functions.
Okay.
The next step from here is going to be how we're comparing our xy to our x dash y dash. You look at function 1, left-hand side, and equate it to function 2, left-hand side. Y dash is equal to y minus 6 on 3. That's equation 1. Then you compare the right-hand sides. The right-hand side of equation 1 equals the right-hand side of equation 2. After simplification, that's what that ends up looking like. Fair enough?
Okay. Yeah.
Cool. That gets us x dash y dash equations. If it's not already rearranged to have x dash y dash in the on their own, then do so. In this case, we have a little bit of a special scenario because where we're going has no transformations on it, so there's no rearranging to be done. So depending on what format your question is asking for the answer in, this might just be it where you finish, right? You know this is x dash, so that's my new x. This is y dash, so that's my new y. This is a perfectly valid way of expressing a sequence of transformations right then and there. But a lot of the time they want it in English rather than in math notation. So that's what step 4 is going to be showing you how to do. And it is by far the thing that you have the most freedom on. There are so many ways of doing this. So I don't know, have you done these questions before, looked at the answer and like seen something completely different?
Yeah.
The fact of the matter is you might not have actually gotten it wrong, because there are several ways in which you can do transformations that still get you to the same spot. Even if we just think about like moving a point along a Cartesian plane. Like let's say I have the point 1, 1, and I want to move it to 2, 2. Well, I can move it right 1 and then up 1, or I can move it up 1 and then right 1. The order of which I do that doesn't actually matter. I can multiply it by 2 in one direction, multiply it by 2 in another direction. That's using dilations as opposed to translations. So it might be the case that you've done a right thing, but the book has just shown you one possible way of doing it. So here's my possible way of doing it. What you've been taught may differ. It may be perfectly fine. This is just the way that I've decided to present things because it's, in my opinion, as close to what you do in like your function graphing versus any other method. But anyway, how does it actually work? So if you're going to do it the way that I'm suggesting you do it, first start by making sure any coefficients on the x and the y are removed, factorized out the front.
Okay.
So there's nothing going on here, so nothing needs to be done. Technically there's nothing to be done here as well, but let's just make it super obvious. Taking that division of 3 and like really making it sure it's out the front. These are, of course, still the same thing though. When you do it this way, you write the transformations in the order of translation, reflection, dilation. Most people are being taught doing the other way around, D, R, T. That would require a different step A. So just for what I've written here, if you do it in this sort of procedure, you do T.
Yeah, I think in my school we've done dilation, reflection, then translation.
Yeah, it's pretty common to do it that way. I can show you, if you're already familiar enough with that, I'll show you how to modify it for DRT if you prefer.
Yeah.
Sure. You just got to know how to do one of them, and that's it, really. So if you've already got stuff to do if you're already familiar enough with DRT, I'll just show you what to do there. So instead of what I've written in part A, where you factorize it off, in part A, if you're doing DRT, you now need to expand it through. So still x is going to be whatever, x dash equals x minus 1. There's no coefficients involved. We had y dash equals y minus 6 on 3. That now needs to be written as y over 3 minus 2. You expand everything through both of the terms. When that is done, you can now do it in the order d, r, t. And so we're just going to do exactly that. First things first, are there any dilations? Well, there's one here. It's a division of 3, so the dilate factor is of a third. You could say from the x, you could say along the y, because again, this is on the y dash thing. I'll just say from x, because that's what the book will typically say. No more dilation factors. We now move on to reflections. There's no multiplications of negative anywhere, so we move on to translations, which we can do in any order, right? So any one of these individual categories, you can do the x then the y, or you can do the y then the x. It doesn't actually matter which order you do them in, as long as you're doing it specifically in d, then r, then t. That's the main thing. Again, that goes back to my example of shifting right by 1 and then up versus up and then right. It's the same thing. So let's just do translate down by 2 and translate left by 1. So you just got to keep in mind that when you're using x dash y dash stuff, the numbers that you're seeing here are the factors themselves. Those are the things that you write. And I'm using arrows just for shorthand. Don't actually do arrows in your SAC, because if you have a look back at the screen share, you'll see the proper language of it. And I guess I'm just being a little bit lazy. If you see a translate of 1 unit in the negative x direction, translate 6 units in the negative y direction, that's the kind of wording they're looking for on that. But I mean, my handwriting isn't the greatest.
Can I annotate on the screen? I want to press another question. Like I'm wondering, like if there's like a 3x minus 2, do I express it as first a translation of x minus 2 followed by dilation of 3?
So hang on, so start me off again properly. So what's the modification?
3x minus 2.
So x dash is 3x minus 2 and y dash is the same as what it was?
No, like the equation is 3x minus 2.
Oh,
so to go from
to
go from x to 3x minus 2, do I first like translate it? Do I add a translation of minus 2 first, like x minus 2, then followed by 3x?
So what you're describing there would be an approach that's less about x dash y dash and more about doing it by recognition. Are you intending to use x dash y dash here, or are you just trying to figure out how to go from one to the other?
I think I'm trying to go.
Because both work. Both work. I'll just show you how to fix it up if you want to do the other way.
Yeah, well, I think I have to try and use the x dash y dash.
Okay. So if you have to use x dash y dash, you're going from here to here, yeah? So if you're using that, my first recommendation is if we're going from y equals x to 3x minus 2, we're going to use our x dash y dash notation on the thing that we're moving towards, yeah?
Okay.
This has no transformation factors, so there's nothing involved there. Linear, oddly enough, is the weirdest one because, like, you know, what's a y transformation, what's an x transformation? This is a shift down by 2, we know that much, so we can move that over to the other side. Typically what you end up doing is you just move everything over, because, if you think about like a f of x, that's usually a dilate factor affecting the y, so we would also move that over to the y side. That would be, where's the steps? So far we've done step 1, which is get our x dash y dashes in there. Step 2 is the rearranging. That's what we just did there. Step 3, we grab the finished products of the left-hand side, make them equal to each other. Y equals y dash plus 2 over 3. And the finished products of the right-hand side, make them equal to each other. X equals x dash. Then from there, rearrange to get x dash and y dash on their own. That's what step 3b tells us to do. 3y minus 2 equals y dash, and well, that's already there. Then from there, since you're doing DRT, I want to make sure everything is expanded all the way through, which it is. And then we go ahead and do our procedure. So in this case is a dilate of 3 from x or along y, and a translate down of 2. So when you said the 2 factors, you were right in the sense that those are the things that are involved. A shift down by 2 and a dilate of 3 is involved, but the order in which you do that matters. To highlight that, I have a point out here. It's going to be 2, 2. If I apply a shift down first of 2, that'll put my point here. And if I then multiply that by 3 in the y direction, it'll stay exactly where it is. Versus, if I do the opposite, I start my point up here in 2, 2. Dilate first, we'll shift it all the way up to 3 2s are 6, and then shift it down by 2. It's now going to end up 6 5 4. So the order in which you do these things matters, especially because you're comparing multiplications and subtractions and additions to each other. They impact things in different magnitudes. So if you're being required to use this x dash y dash stuff, this is how I would go about it. There is a perfectly valid way of looking at this and knowing off rip what your factors should be, but again, if you're supposed to use x dash y dash, then just stick with this then.
I'm still confused.
Still confused?
Yeah.
Whereabouts did I lose you?
Okay, so 3x minus 2, like, to me it sounds like, oh wait, okay, I think I read it.
So is the confusion why can't it be the other way around?
Well, it was, yeah.
Yeah. So
yes, so when I'm transforming one equation, one function to the other, I'm going to do it from outside in, but when I'm like finding the image of a point, or going from one to the other, sorry, if I want to find the image of a point after the translation, I have to go from outside, sorry, inside out.
I'm not too familiar with what you're considering to be the inside and the out.
Like from x, like 3x is like inside, and minus 2 is outside. It's a different term.
It's less about that, I would say. I'll show you why you can only do this one way. So when you're applying transformations, you are now using the shortcuts of things. So let's say I'm doing applying a translation down first, right? The basic form of a translate downwards is f of x minus a, whatever the translate down is. So I just take whatever my function is, x, and then tag on a negative side of whatever that is at the front. That's going to go into y equals x minus 2. Then, if I want to apply my dilation, the rule for that is this, a f of x. But this is f of x now, not this anymore.
Yeah.
So if you then go to dilate, it's got to go onto the translate as well. So what you're highlighting, I think you are noticing something, which is the rules for, there seems to be like two separate types of questions. And sure enough, I have two separate documents on them. So the difference between them is one is where you know the sequence of transformations that you have to apply. That's what you're talking about when you're finding the image of a point or a function, right? You have a whole bunch of stuff that you want to apply. That's when you're following procedure one, which is shove it all, basically this sort of thing, right? Get your x dash, y dash sorted first, and then shove it into a function. The other type of question is where you have two functions, you know nothing about the transformations beyond what you could maybe glean from looking at it, and you're told to figure out what's the sequence or what's a sequence that gets you from one to the other. So if it says find a sequence, that's document 2, following this procedure. If it says find the image, or sketch the image, or whatever, find the rule of the image, that's document 1, which is this sequence here. There's only minor nuances between the two. Fundamentally, it just goes down to whether I want to rearrange for x dash y dash, or whether I want to rearrange for x and y. And yeah, it's a matter of basically whether you want to get the x dash y dash on its own, the transformation, or x and y, because you need to do that to shove it into a function. Fair enough conceptually?
Yeah.
We'll do some more examples just to get your head around it. Was there any one of these types of questions you wanted to focus on, or should I do like a...
Yeah, determining sequence. I think I'm still confused on that.
Yeah, certainly. So let's do that.
Could you give me a second? I'll just do
Yeah, man.
one thing.
Yeah, go for it.
Yeah, but
Wait. Okay, so we'll just rip straight off from 3E question 1. So let's give that a shot. I'll start writing it down anyway. I'm zoomed out quite far. Let's fix that. Okay, so we want to take the graph of y equals x cubed and move it towards the graph of y equals 2 bracket x minus 1 all cubed plus 3. So starting here, ending here. That's our goal. I'll leave the procedure to follow, and we'll update step 3b. I'll jump in there just to make sure we do that right for DRT instead. But for now, let's see how far you can take it. What's our first thing that we should be doing?
so the original function and the new function. So original is x cubed, and the function we're trying to go to is 2x minus 1 the whole cubed.
Yep. So why
That's
does that
true.
matter? What are we clarifying there?
X dash and y dash.
That's it. We're going to give y dash to the new one. Good so far? What do we do now?
We have to find the transformations that are affecting x and y.
Yep, that's it. How are we going to do that?
Are we going to use the second function?
Yeah, so there's nothing really on the first function, so we can leave that one alone. Second function's got a bunch of stuff on it. What needs to be moved?
So we can move the plus 3 and the dilation of 2 to the other side.
Exactly right.
Is that it? Or Is there more?
What do you think? I'll let you lock in an answer. Does anything else
It,
need to move?
it doesn't look like I can do anything more
Yeah, and I
without
would
it
agree there.
looking different.
Yeah, because
So that's it.
yeah, what I mentioned before, right? Don't you can move over as much as you can, but no more than would break the function. You know, like cube rooting this, suddenly you're turning it into a linear as opposed to a cubic. So yeah, you've got a good intuition for when to stop. Yep, well
Can you
that's
give
that.
me a second? I'll just copy it down.
Yeah, go for it.
Yes.
Sweet. All right, so we got
Um,
to step 2 completed.
yeah. So now we've got to make y equals to the left hand side and x cubed equals to the right hand side.
That's it.
Oh,
Yeah. So that's grabbing
okay.
left equals left and right equals right. Absolutely. Y equals y dash minus 3 on 2. X cubed equals x dash minus 1, all cubed. Yeah. What else? I'll let you finish writing.
Oh, yeah. Okay. So are we done with step 3 or?
Well, what have we done so far in step 3? What's it say?
What? Equate the x component to each other and the y component to each other for A.
Mm-hmm. Sounds
Would
pretty good to me.
be, yeah. What do I do for B? Like a rearrange for x dash y dash.
Yep.
Oh, do I have to like make those the subject?
Make those a subject. Correct.
Yeah.
Yep.
Okay. So y dash would be 2y minus 3 plus 3.
Yep.
And x dash would be x minus 1. So x plus 1.
Yep. Both of those good. That'll conclude the step 3 there. Step 4, if you haven't already made a note for yourself, if you are like copying down these or whatever, instead of removing coefficients, you want to make sure it's all expanded instead. So, do we have to do anything here?
Um,
At least for part A, which would be to make sure everything's expanded out.
no, yeah, I mean we've got nothing to do.
Yeah, that's it. It's already expanded. No, nothing required here in this case. So for your case, that'll be your part A being done. Part B should now read DRT instead of TRD.
Okay. Can you give me a second? I'll just write notes for myself.
Yep.
Okay. Yeah.
Sweet. Okay, so we know we have to do in the order of D, then R, then T. Yeah, what are we going to start writing?
So we're going to look at the dilations
Yep.
on X and Y. Right.
Which ones, if any, do we have?
So there's two Y's, so
Yep.
It's a dilation from the x-axis.
Yep. Dilation from X by factor what?
2 units.
Yeah,
Oh,
you probably just say by factor 2. Dilation from X by factor of 2. Units is more so like reserved for translation stuff. But
Okay.
otherwise, yeah, that's good.
Okay, I'll just write this down.
Yep.
Okay, so reflections. There are no reflections.
That's correct. Yep.
And translations, there are two translations. So
Mhm.
x plus 1, so that's translation of 1 unit to the right.
It is 1
Wait,
unit to
no.
the right.
Wait, no, that's left, right?
So this is the weird bit, right? It's when you have x dash y dash, everything works as you think it should. Like the numbers you see here are exactly what is happening to the point. The reason why you've been taught that x minus is right is because when you shove it into a function, we get that flip happening. Like if we look back at the even if I take it back to the dilation example, remember how I was talking about dilations for x appear as division? At least when it's shoved into the function, it's because when you follow that procedure of getting the x and y back on their own, things flip over. But if you go all the way back to your x dash y dash like fundamentals, and we look at translations, you're starting at some point and you are in fact adding to that point to shift it. It just so happens that when you follow the procedure of shoving it into a function, there's no further rearranging to be done. You know, you rearrange to get the x, that makes it look like a minus when it goes into the function.
Okay, so when we're putting it into a function, we have to do it in terms of x, not x dashed.
Yes, because functions use y and x is the easiest way to think about it. Because you're starting with your original y equals f of x to see what's happening when you apply something new, we do substitution. But obviously substitution requires you to have the same letters. So you do a bit of a rearranging first.
Okay.
Yeah.
Yep. Okay.
Those are the fundamental differences between applying versus determining. Applying, you want to get x and y and shove that into a function. Determining, you want to get x dash y dash and then expand that out into your English description of the transformations.
Okay. So okay, so there will be a translation of 1 unit to the right.
Yep, 1 unit right. You should be able to get away with saying 1 unit right. The textbook will say 1 unit in the positive x direction. It is a lot more writing.
I've inquired about that, and my teacher says that it's okay if I write it like
Easy.
that.
Yeah, cool. If your teacher signs off on it, perfect. Stick with it. Translate 1 unit right. What else?
Okay, translation 1 unit right, and there's going to be 3 units up.
That's it.
3 units down. Or
Nah, so it doesn't go opposites. It's just that it goes back to what you would expect things to be. So, adding
okay.
1 to the x should move it further along the x. Adding 3 to the y should move it further along the y.
Okay.
Yeah, it's I know, because like when you learn about quadratics the first time, 'cause that's when things get a bit weird. When you start having to worry about x minus being a shift right. It's like year 9, year 10, maybe. And you have like that many years of it being drilled into you that x minus goes right, and then they shove x dash in front of you, and it's like, oh shit, now I'm going back to this. Which is kind of why I've written the notes in a way where I'm trying to keep it as related to functions stuff as possible. That's where we had a bit of a difference in determining the sequence. Like, removing those coefficients. That's what you do when you sketch functions. You want to take the dilation factors off so you can see what the actual transformation looks like under the in the function notation. Because like, if you had, for instance, y equals bracket 3x minus 2 all squared, that is not a shift right by 2. It is in fact a shift by minus 2 on, yeah, exactly, 2 on 3. You want to reveal it. And, that's what I'm trying to do with the notes in the transformation bit. But there's, pros and cons, right? If your teacher's teaching one thing and I'm teaching another, that's also a bit of a problem. So it's kind of like a pick your poison. But I mean, look, this looks pretty good with what you had done. I don't think I'd really, maybe up until this bit where we were explaining how the translations work, as far as how to interpret them. I think everything else you did without me really saying much. Where did I jump in? The only times I said things was to just get you to reread the steps and then come to your own conclusion. So you should be pretty happy that you got through the gist of it up until literally just the translations there. Sound fair?
Yep.
Cool. Let's do another, unless you want to do something else.
Yeah, can we do another one?
Yeah, let's do another. Let's even move to a different section so we can use a different type of function. Let's go with this. Let's go with this hyperbola 2c. So we're starting at y equals 1 on x minus 1. Oh, this is a truncus actually. What am I saying? X minus 1 all squared minus 6. And we're moving towards, yeah, okay, it's also untransformed, y equals 1 on x squared.
Okay, so the destination function will be y dash equals to 1 by x dash squared.
Yep, perfect. Getting the notation right, and then yeah, nothing needs to change there. Sweet, that's that.
Okay, so y dash will be equal to y dash.
Y dash equals y dash.
Right?
I think you skipped ahead in the steps.
Oh, oh yeah, yeah, so y minus, on the first one it's going to be y minus, so y plus 6.
There we go, that's better. Getting all the y transformations onto y side. And then you can do what you were doing before, which will now look like what?
Yeah, so y dash equals to y plus 6.
Yes.
And x, 1 by x dash squared will be equal to 1 by x minus 1 the whole squared.
Mm-hmm. Cool. When you finish writing that, I'll let you take it off from here.
Okay, so Yeah, step 2 is done. Step 3 is okay. So we have to make sure it's expanded. Okay, no. We've got to make x dash and y dash the subscript.
That's it. Good
Yeah.
catch.
So we can do cross multiplication.
Yep. Cross multiplication. So that would
Dash
get.
squared equals to x minus 1 whole squared.
Say that one again, sorry?
X dash squared equals to x minus 1 the whole squared.
Oh, yeah. Yeah, okay. That's good.
I'll just write that down. Okay, so we can simplify that by canceling out the squares.
Yep. Pretty good.
But now, yeah, it's done. The step's done.
Yep, that step is done. That's good.
Yeah, step 3 is done. So step 4, make sure there are no coefficients. Yeah. And
Well, so remember your step 4 looks a bit different to what I had written. So you want to have yours expanded rather than removed.
yeah, expanded. So it's expanded. And
It is expanded,
now
yep.
we like the transformations and all that. Dilation, reflection, and translation.
Pretty good.
So there are no dilations and reflections.
That's correct, yeah.
So the translations are 1 unit left.
Yep.
And 6 units up.
Yes. Perfect. Yeah, no comment. You did the whole thing. You can even then, as like one thing I can suggest, you can even then just look back at your original functions and then look, hey, does my sequence look like it does what I think it does? Right, like if I'm starting here, does what I just said make at least enough sense? When there's dilations involved, it can be a bit hard to see, but if there's purely just transformations, or translations rather, 1 unit left, well, it was 1 unit right, so bringing it 1 left should definitely get rid of that. And then it was 6 down, so 6 up, that seems about right. So you can do a quick little sanity check to make sure, hey, did my sequence actually look like it works? Cool. Yeah, that's x-y stuff. That's the approach that you follow there. But as far as the actual work, I know there was a lot of steps written there, but if you ever look at like the actual work that was done, this is already told to you in the question, so you don't write that line down. You rewrite one of the functions, maybe 2. So you do this line. So 1 line, 2 line, 3 lines of work, and then you write your conclusion. So lots of steps, yeah, but each individual step is fairly trivial. Cool?
Yep.
Okay. We've still got a bit of time left. Is there anything that needs further clarification? Did you want to try and smash out another example? Anything new?
I think that's about it.
That's about it? Sure.
Yep.
I can take you through another example if you like, or if you're happy with where we're at, we could just call it a bit early and I can give you 4 minutes back of the day. What would you rather do?
Okay, could you give me a second? I'll just check through my textbook
Yeah, go for it. Yeah.
to see if I think. Okay, I don't think I have any problems.
Yeah, I mean that's a good a good problem to have, to not have any more problems right now. So yeah, you got the procedure that you need to follow for these, and the good thing about it is it doesn't actually even matter what the function is. We saw truncuses, we saw roots, we didn't actually do any, but there are in the book. All the polynomials that have that inflection point form or turning point form doesn't actually matter, because the simplification steps, because they're the same function on either side, they pretty much all just cancel into each other and become linear every single time at the end. So it's fairly chill, as long as you've just got the main difference, which is if you're applying or finding the image, the rule of the image, however they write it. That's one procedure. We didn't really touch on much of that today. We touched on more when you have just the functions themselves and you're told to figure out how to go from one to the other. Cool. Alright, I'll leave you to it. If anything comes up, feel free to let me know. We can do it some time on like a Friday for the review class to touching up any lingering questions. Otherwise, I'll leave you to enjoy the rest of your day.
Thanks.
Take care.
Good day.